Hello everyone, welcome back. In this video, I will be covering section 6.4, work. If an object moves along a straight line with position function s of t, then the force F of the object in the same direction is given by Newton's second law of motion as a product of its mass and its acceleration. Force equal to ma. Force is a vector, acceleration is a vector. So F equal to m times, here d square s by dt square. If the position is s of t, then the second derivative is the acceleration. The velocity would be ds by dt, the first derivative, and the acceleration would be the second derivative. So force is mass times acceleration, where m is measured in kilograms, and the displacement is measured in meters, and force is in Newton, which is kg, mass times acceleration. Mass is kg, and the acceleration is meter per second square. Kg times meter per second square is considered to be the units for the force. In the case of constant acceleration, the force F is also constant, because if d square s by dt square was constant in this relation, then obviously F will also be constant. And the work done is defined to be the product of F and the distance d that the object moves. So W for work, which is equal to force times the distance here. Work equal to force times distance. The unit for work, W, is Newton meter. So that is what kg times meter per second square is. So it is Newton meter. In this case, F is Newton measured in Newton, and distance is measured in meters. So it is Newton meter, which is called a joule, represented by the single letter J. The equation above defines work as long as the force is a constant. But what happens if the force is a variable, which changes at every point, let's say? Let's suppose that the object moves along the x-axis in the positive direction from x equal to a to x equal to b, and at each point x in between a and b, the force f of x acts on an object where f is continuous function. Then what we do is we divide the interval ab. So you have the force function like this, and let's say it is from a to b, the force changes, the force function changes its value at every point between a and b, let's say, but f of x is continuous here. The values of f don't change very much over one particular interval. As long as we make the interval very small, we take lots and lots of intervals as n approaching infinity. Each interval the force over each interval is considered constant in that case. So Wi, which is the force, which is the work done on the ith subinterval, is the force acting on the ith subinterval multiplied by delta x. The force acting on that ith subinterval is considered to be constant throughout that interval, that is f of xi star times delta x. That is a distance. So Wi, which is the work done on the ith subinterval, f of xi star delta x. We do this for every interval. So we get W, which is approximately equal to sigma I varying from 1 to n, f of xi star delta x. So it will be, we are allowing n to approach infinity. Then it can be, this is nothing but the Riemann sum. This part is nothing but the Riemann sum. Riemann sum is big S. Big S is the elongated S. Elongated S can be converted as can be written as an integral. So it seems that the approximation gets better and better as n becomes large, as n approaches infinity. Therefore, we define work as W equal to limit as n approaching infinity, sigma f of xi star delta x, which is integral a to b fx dx. So a and b are the a and b, or AB is the interval over which the force function is defined. Now let's to do the problems of this exercise, we need the law from physics, law of physics, which is Hooke's law. So we are going to use that Hooke's law to do some of the problems here. So what does Hooke's law say? Hooke's law states that the force required to maintain a spring stretched by x units beyond its natural length is proportional to x. The f of x is k times x. K is the constant of proportionality. X is the length beyond the natural length of the spring, the amount of stretch. It can also be considered as amount of compression if it was related to compression. Where k is a constant called the spring constant. Hooke's law holds provided that x is not too large. So let's look at this picture. So we have a spring and it is of natural length is considered to be at 0. It can be any length, but the natural length. So there is no stretch here. But in this case, in the second case, where if you look at part A of the figure, so there is a stretch. So if you compare it with the previous one, up to 0 is the natural length. Beyond 0 is the stretch, that is x units. So force is proportional to, f of x is proportional to k times x. F of x is proportional to x, which is written as f of x equal to k times x. K is said to be either the spring constant or can be called as constant of proportionality. The stretched position of the spring. So this in the second figure, you notice that up to 0, it is the natural length. So from 0 to x, that is how much the spring is getting stretched. So that is the extra length. So f of x equal to k times x, the amount of stretch. So let's try some problems here. How much work is done in lifting a 1.2 kilogram book off the floor? So one information here, that is the mass. To put it on a desk, that is 0.7 meter high. So here, instead of a horizontal motion, it's a vertical motion here. So we want to put the certain book at a height. So this is the distance moved. So D equal to 0.7 meter high. What is given here is just the mass. Use the fact that the acceleration due to gravity is 9.8 meters per second square. So we will use the first part. We will do the first part. And then the second part is asking us how much work is done in lifting 20 lb weight 6 feet off the ground. So let's try one by one. Part A. So the force is actually extended and opposite to that exerted by gravity. So by Newton's second law of motion, F is equal to mass times acceleration. Mass is here 1.2 kg. Acceleration is 9.8 meters per second square. So 1.2 times 9.8, that is 11.76 kg times meter per second square. The units for force when the system is in meter and kilogram is Newton. So that much Newton. This is just the force. Now we want to find out the work done. That is denoted by W. W equal to force multiplied by distance. Force is 11.76 Newton and distance moved is 0.7 meter high, 0.7. So if you multiply these two, we are going to get 8.2 Newton meter, or we can say it is 8.2 approximately Joule. All right. Now for part B, what is the difference? How much work is done in lifting 20 lb weight? So when the problem says weight, it's already force, because mass times acceleration is the force. When you say weight, weight is already taking into account of the acceleration due to gravity. So in this case, force can be taken as 20 lb, and it has to move 6 feet off the ground. So distance is 6 feet. So work done in moving the object from 6 feet off the ground is actually W, which is F times D, which is 20 lb times 6 feet, which is 120 foot lb. All right. Let's try the next example. When a particle is located at a distance x feet from the origin, the force of x squared plus 2x acts on it. How much work is done in moving it from x equal to 1 to x equal to 3? Here, obviously, in this case, a force is given in terms of a variable, which means that it changes as per distance. So we are going to use the integral representation here. So integral f of x dx is work done whenever you have a varying force. So it is from 1 to 3. So lower limit is 1, upper limit is 3. That is integral 1 through 3, x squared plus 2x dx. If we integrate, it is x cubed over 3 plus 2x squared over 2 between the limits 1 and 3. So it's 3 cubed over 3, which is 9, plus 3 squared, which is 9, minus 1 over 3 plus 1. So it is going to be 18 minus 4 over 3. So here 2 can be taken out. That is 2 times 27 minus 2, which is 25 over 3. So it is 50 over 3. The units were mentioned, then you use the units, appropriate units for W, the work done. Try the next example. A force of 40 Newton is required to hold a spring that has been stretched from its natural length of 10 centimeter to a length of 15 centimeter. How much work is done in stretching the spring from 15 centimeter to 18 centimeter? So the first information is to find the constant K. So what is the force? Force is given by, if it is varying force, it is equal to K times X by Hooke's law, right? So it is proportional to the amount of stretch. The force is proportional to the amount of stretch. So if I use 40 Newton here, remember, whenever you use Newton for force, the length measured should be in terms of meters. So it has been stretched from its natural length of 10 centimeter. So natural length of 10 centimeter to a length of 15 centimeter. So this is its natural length. It has been stretched to 15 centimeter. So there is a stretch of 5 centimeter. What is the stretch? From the natural position, it is 5 centimeter. So that is the stretch amount. So that is, a 5 centimeter actually is equal to 5 over 100, which is 0.05 meters. So it is K times 0.05. So what is K equal to? 40 divided by 0.05. Which will be 800. So the first part is only to find the K. Now we do the second part. How much work is done in stretching the spring from 15 centimeter to 18 centimeter? When you say 15 centimeter to 18 centimeter, the natural length is 10 centimeter. The stretch here is 5 centimeter. The stretch here is 8 centimeter. So we will do work done, which is integral f of x dx. The first stretch is 15 centimeter, that means 5 centimeter from the natural length. 5 centimeter equal to 5 over 100 meters, which is 0.05 meters. Because we already know that force is measured in Newton, it is important to convert the distances or the stretch from the natural length in terms of meters. Then 8 centimeter stretch equal to 8 centimeter over 100, which is equal to 0.08 meters. So it's 0.05 to 0.08 f of x d of x, which is integral 0.05 to 0.08. K is 800, so it's 800x, kx. That is 800 times x square over 2, 0.05 to 0.08. That will be 400 times 0.08 square minus 0.05 square. That is 400 multiplied by, if you compute this 0.08 square, minus 0.05 square, that will be 0.0039. Outside you have 400. So if I convert this to decimal, it becomes 1.56 joules. .0039. All right. Let's try problem number 3. A variable force of 5 times x to the negative 2 moves an object along a straight line when it is x feet from the origin. Calculate the work done in moving the object from x equal to 1 foot to x equal to 10 feet. So the force is varying, which is 5 times x to the negative 2. And then the question is, calculate the work done in moving the object from x equal to 1 to x equal to 10. So work done by the formula is integral a to b. So x varying from x equal to 1 to x equal to 10 feet. And the force f of x dx, force is given by 5 to the exponent negative 2. So 5 can be taken out of the integral sign. It's x to the negative 1 over negative 1. When you integrate, you have to plug in 10 and 1 for upper limit and the lower limit. So it is negative 5 times 1 over x between 1 and 10. So it is negative 5 times 1 over 10 minus 1. So it is negative 5, 1 minus 10, so negative 9 over 10. So which will be 45 over 10, which is 4.5. Because we are given feet and the variable force is considered to be in terms of lbs. So we can consider work done as foot lb. Let's try number 9, which is also on the practice exam. Suppose that 2 joules of work is needed to stretch a spring from its natural length of 30 centimeter to a length of 42 centimeter. A, how much work is needed to stretch the spring from 35 centimeter to 40 centimeter? B, how far beyond its natural length will a force of 30 Newton keep the spring stretched? So if you look at the first statement, suppose the 2J of work is needed to stretch a spring from its natural length of 30 centimeter to a length of 42 centimeter. So we are going to consider the work done. This is already given to us. Work done is integral fx dx, right? resistance party, fx dx, and we are not given constant of proportionality, but we are given that it is this 2j work is done, which helps to stretch a spring of its natural length 30 to a length 42 centimeter. So natural length to new length is 30 to 42. So what is the stretch? Stretch is going to be 42 minus 30, which is equal to 12 centimeter. So this position is 30, let's say, natural length, and it stretches to 42. So this is the amount of stretch. That is going to be 12 centimeter. So we can say 0. What is 12 centimeter in terms of meters? So 12 over 100. So that will be 0.12 meters. So the actual stretch is 0.212 meter. Because f of x is, the work is given to be in joules, that means it is in Newton meter. So force must be measured in Newton and distance must be measured in meters. So this is given to be 0.12, and we'll assume this to be k times x. And this information helps us to find what k is. So this is already given to be 2. So 2 equal to, k can be taken out of the integral sign. When integrate x, it is x squared over 2 between 0 and 0.12. So it is k over 2, and it's square of 0.12 minus 0. So k over 2, 144, it will be 0.0144. If you solve for k, you have to multiply by 2. If you solve for k, it will be 2 times 2, 4, divided by 0.0144. That is the value of k. That k will turn out to be, this will be 2500 over 9, which is approximately 277.78 Newton force divided by meters. Newton over meter. So this is the first part. We can even keep it as fraction, which is 2500 over 9 will be a better figure, so that we need not have to have the decimal value there. So for part B, it's asking how far beyond its natural length. So it is, the question is asking for the amount of stretch, right? So it is asking amount of stretch. Will a force of 30 Newton keep the spring stretched? So 30 Newton, so force equal to k times x. Force is given, in this case, that is equal to 30 Newton. And k is already found out, which is 2500 over 9. And you want to find out what x is. So x equal to 30 times 9 over 2500. Thirty times 9 30 times 9 divided by 2500, that will be 270 divided by 2500. If you reduce and if you find out what this value is, it will be 10.8. And that this will be in terms of meter, because all other units in the problem are given in terms of centimeter. If you multiply that by 100, this value by 100, you will get in terms of centimeter, that will be 10.8 centimeter. So 27 over 250 meters equal to 27 over 250 meters times 100. That will be in terms of centimeter. So that is the amount of stretch. Okay, in this section, there are other videos you may want to verify with the section videos. This problem is done in the video 7. Number 7 is done in the video, chapter video. Then 9 is done in this video. 3 is done in this video. And 15 is done in the chapter video. So you may want to verify these problems. Hope this video helps. So watch my next video on 6.5, which is average value of functions.